Now, let's see how to solve the problem using a short line of 40 kilometers long. Let's consider a 220 kV three-phase transmission line. The resistance of the phase per phase is 0.15 ohms per kilometer, while the inductance is 1.3263 millihenry per kilometer. So the shunt capacitance is negligible since it is a short line. So we will use the short line model that we have learned in part 1 to determine the voltage regulation and the efficiency of the line, etc. For different cases. For case A, the load is 381 MVA at 0.8 power factor lagging at 220 kV. And for the part B, we will consider the same load, but at power factor lagging, leading at 220 kV. So for the first case, we have the series impedance of the line. We multiply the impedance per kilometer times the length of the line. So we have here 0.15 plus 2 pi j times 16, which is the reactance, times the inductance. This is the reactance, times 40 kilometers, and it will give us 6 plus 20 j, the total impedance of the line. The receiving end voltage is per phase is 220 divided by square root of 3. We consider here as a reference with shift angle 0. The apparent power at the receiving end is found to be 381 with angle 36.87. So we have 304.8 megawatt plus 228.6 megabars. The receiving end current, as explained in the previous part, can be calculated using this formula, and it is found to be 1000 with minus 36.87 degrees. It is lagging the voltage by minus 36.87. So let's see Vs. Vs is equal to Vr plus ZIR, and it is equal to 144.33 with angle 4.93. So the line-to-line sending end voltage is equal to square root of 3 Vs. It equals 250 kV. And apparent power at the sending end is found to be 433 with angle 41.8 MVA. The voltage regulation, we apply the rule. It is 250 minus 220 divided by 220. 250 is the no load receiving end, which is the source, the sending end voltage, minus the full load, which is 220 kV. So the regulation is found to be 13.6%. Let's see how to calculate the transmission line efficiency. The power at the receiving end, as we have seen, it is equal to 304.8, and the power at the sending end, it is equal to 322.8. So the efficiency of the line is 94.4%. So we will apply the same for the case where we have a load of 381 MVA at 0.8 leading power factor. We will apply the same approach. We will calculate Vs, then we calculate the line-to-line voltage, the apparent power at the sending end, and then the percent voltage regulation. Here we have the voltage 121, it becomes 210 line to line, minus 220, which is the rated voltage at the receiving end, divided by 220, it was minus 4.43, and the efficiency is found to be equal to 94.4%.